Just as with distributions, we can talk about partitions by telling their type. The type will just tell the sizes of the sets in the partition. An example would be talking about a partition of 7-element sets of type 1, 2, 1, 2, 4. And it's always necessary when we talk about the type, whether it's a distribution or partition, that the 1 plus the 2 plus the 4 is the total size of your original set, in this case 7. So a partition of a set of 7 elements, say the set 1, 2, 3, 4, 5, 6, 7 of type 1, 2, 4 is just a partition into 3 sets. One of them has 1 element, one has 2 elements, and one has 4 elements. Here's an example of a partition of this type. Our question is, how many partitions are there of this type? How many partitions are there of a 7-element set into 3 parts, one of them of size 1, one of size 2, and one of size 4? And it's very straightforward how to solve this problem, since we already know about distributions. If you tell me a distribution of this type, think of that as a way to put the 7 balls, distinct balls, into 3 boxes. With 1 goes in here. I'll just write out 1, I mean 1 of the balls. 2 of the balls go in here, and 4 of the balls go in here. If you tell me a distribution, any distribution that is of this type, I claim that uniquely tells me a partition of type 1, 2, 4 as well. Just take the set that land in A, the set with just 1 element in it, that's our 1-element set. The set of things in B is a 2-element set, and the set of things that land in C is a 4-element set. There you go. You can think of that distribution as uniquely defining a partition. Furthermore, if you tell me a partition into 3 sets of size 1, 2, and 4, you could just think of the set of size 1 as being box A, the set of size 2 as being box B, and the set of size 4 as being box C, and that would then uniquely determine a distribution of this type. There's this one-to-one correspondence between distributions and sets for this type of distribution, and we can count them easily. How many are there? Well, that's what the distribution numbers tell us. The answer is the distribution number 7, 1, 2, 4. I won't write it here, that's just 7 factorial over 1 factorial times 2 factorial times 4 factorial. Let's look at some other examples. How many partitions are there of a 7-element set into 3 parts, but now we'll have one of size 1, one of size 3, and another one of size 3. In other words, 2 different ones of size 3. We call that a partition of type 1, 3, 3. Well, let's say I take a distribution of 7 balls into 3 boxes. I won't draw the balls separately. Let's say we have A here, we have box B here, and we have box C here. To give you an example of a distribution, I'll just put the balls in here. Here's ball 1, say. Here I'm going to have 3 balls. Let's say it's 2, 7, and 3. In here I'll have the 3 balls, and what we have left is exactly 4, 5, and 6. So you can see what I've shown you here is a distribution of 7 balls into the 3 boxes. And that distribution does give me a partition. I can think of this distribution telling me a partition where the 1 is in a singleton set, the 2, 3, and 7 are in a set of 3, and the 4, 5, and 6 are in a set of 3. But here's the small problem. There's another distribution that will give me the exact same partition. The distribution that has ball 1 here, the one that has ball 4, ball 5 and ball 6 in box B, and ball 2, 3, and 7 in C. These are different distributions because you have different balls going in boxes B and C, but if I just naively translate them into partitions, into these exact sets, the set of things in A, the set of things in B, and the set of things in C, we get the exact same 3 sets. The basic idea is that in a partition, you can think of the boxes as being identical. There's no difference between 2, 3, and 7 in box B and 4, 5, and 6 in box C, or 2, 3, and 7 in box C with 4, 5, and 6 being in box B. You can think of then partitions as being distributions of distinct balls into identical boxes. You can think of box A being just like box B and box C, but because A has only one element in it, that fact alone, I like to use this word, distinctifies it. It makes it different from the others. So how can we get the answer? Well, every partition will correspond to 2 distributions in exactly this way. Whatever you have in box B and box C, you'll get one distribution. And if you just switch the order of B and C, switch the balls in B with the balls in C, you get a different distribution leading to that partition. So the answer here will be exactly this distribution number, 7, 1, 3, 3, and we have to divide by 2. Let's kick this up a notch. How many partitions are there of a 6-element set into 3 parts, each of size 2? That is, how many partitions are there of size 2, 2, 2? Well, let's say I have a 6-element set, 1, 2, 3, 4, 5, 6. And again, I think about distributions. Think of 6 balls. 1, 2, 3, 4, 5, and 6. And let's imagine that I'm putting them into boxes A, B, and C. I could put 1 and 5 in A. I could put 2 and 7 in B, and then I'd be left with 3 and 4 in box C. Now, I could think of this distribution naturally giving me a partition, the set 1, 5, the set 2, 7, and the set 3, 4. That's a legitimate partition of type 2, 2, 2. Why do I have a 7? There is no 7. Change the 7s to 6s. I was writing 7s the whole time, but they should be 6s. So if I just change all my 7s to 6s, I get a legitimate partition of the set of balls 1 through 6. But just like before, if I switch the order, I take a different partition, and I switch the order, not the order, I would switch the balls in box A with the balls in box B. Different distribution. Say A might have 2 and 6, and B might have 1 and 5. And let's say for this example, I keep C with 3 and 4. That's a different distribution, but it leads to the exact same partition. I could also switch around B and C. In how many ways can I switch the distributions, have different distributions that lead to the same partition? Well, it should be pretty clear that any way of rearranging the boxes A, B, and C, think of as rearranging the balls in the boxes, would lead to the same partition. So the total number of distributions of type 2, 2, 2 is just 6, 2, 2, 2. That's the number of distributions, and I have to divide by 3 factorial, or 6, which is the number of ways I can rearrange these boxes to get different distributions and yet keep the same partition. So this is the number of partitions. So The question we should always be asking once we've done a bunch of examples is, can we generalize this? And the answer, of course, is yes. That gives us standard problem 15. It says for a given set, find the number of partitions of a given type. So here we're only interested in partitions when you tell me the type. If the set has m elements, we can talk about a type m1 through m sub n. That's a partition into n non-empty sets. And I claim the answer is just this distribution number, m, m1, m2 through mn. But you have to, as we've seen before, divide by something. What we have to divide by is r1 factorial, r2 factorial, r3 factorial, etc. Where what are the r's? The r's tell you, r1 tells you how many of these m's are the number 1. In other words, how many sets do we have in our partition of size 1? R2 tells you how many sets you have of size 2, etc. In the previous problem, R2 would be 3 because we had 3 sets of size 2. R3 tells you how many sets there are of size 3. I put ... because you can have as many of these as necessary, but it'll be a finite product because, of course, there are a finite number of balls. There'll be only zeros after that, and by zeros I mean 0 factorials, which are all 1, after you get to a certain point, because there's a total of m elements in the set to begin with. So beyond a certain point, all of the r's are 0, so all of the r factorials are just 1, and we can ignore them in the product. So it's kind of written like that could be a large number of things, but it's not a problem. It's just notation that will help us express what we want to express. So this is the generalization, and the reason this is true is exactly the same as we've had before. If R1 is 2, there'll be 2 different rearrangements of those 2 boxes that, say if you create distributions of the same type, there'll be 2 rearrangements of the 2 boxes that contain only 1 element in them. Both will give you the same partition when you convert a distribution into a partition. If R2 is 9, there'll be 9 factorial rearrangements of the 9 boxes that get 2 elements each in them, and thus you have to divide by 9 factorial when you convert distributions to partitions, because there will be 9 factorial distributions that all lead to the same partition. And that would be true anytime you have repeats in the sizes of the different sets in your partition. So it's a little bit tricky, but the formula is pretty straightforward, and you'll see that this formula matches what we've computed in the examples above.